Two of the most precise instruments ever built are looking at the same universe and returning two different answers. The Planck satellite, measuring the faint afterglow of the Big Bang, says the universe is expanding at about 67 kilometers per second per megaparsec. The Hubble and James Webb telescopes, measuring exploding stars in nearby galaxies, say it's closer to 73. Both cannot be right. This was supposed to be resolved a decade ago. It has gotten worse. The disagreement now sits above 5 sigma, the statistical threshold at which physicists stop calling something a measurement error and start calling it a problem with reality. Every new instrument built to close the gap has widened it, and what most people were told in school, that the expansion rate of the universe is a settled number in a settled model, is quietly no longer true. You were promised a self-correcting universe. What you are actually watching is physics running out of ways to reconcile itself. Two measurements, same cosmos, different answers. And the harder scientists look, the further apart they drift. Here is the part that should bother you. If the Hubble constant is not constant, or if both of these numbers are somehow correct in different regimes, then the standard model of cosmology, the framework called Lambda-CDM that every physics textbook rests on, has a hole in it that no amount of better data will patch. The age of the universe you learned, the dark energy percentage you memorized, the size of the observable cosmos, all of it depends on a number that refuses to agree with itself. Before we go deeper, tell me where you're watching from and what time it is, and be honest with yourself. Were you ever told, in school or anywhere else, that the expansion rate of the universe was still unresolved? Most people weren't. That silence is part of the story. The version most people absorbed goes something like this. Edwin Hubble discovered in the 1920s that distant galaxies are moving away from us. The universe is expanding. Later, satellites measured the leftover heat from the Big Bang with astonishing precision. The story was closed. The textbooks were written. Move on. That story leaves out the last 10 years. Background: the faint radiation left over from about 380,000 years after the Big Bang. Planck reported a Hubble constant of roughly 67.4 kilometers per second per megaparsec. It was one of the most precise measurements in the history of cosmology. The community expected the local measurements, done with nearby galaxies, to eventually converge on that number. They didn't. By 2019, the SHOES collaboration, led by Nobel laureate Adam Rees, using the Hubble Space Telescope to measure Cepheid variable stars and Type 1a supernovae, reported a value near 73. That gap of about 9% might sound small. In cosmology, at this precision, it is enormous. Then came the excuses. Maybe the Cepheids were miscounted because of crowding. Maybe the dust corrections were off. Maybe the local sample was biased. Reasonable objections, testable ones. In 2023 and 2024, the James Webb Space Telescope, with resolution far beyond Hubble's, went back and looked at the same Cepheids. The crowding hypothesis died. The distances held. Independent methods, the tip of the red giant branch, mirror variables, surface brightness fluctuations, all clustered near the same higher value. Think about what that timeline actually shows. 12 years of instrumentation upgrades, multiple independent teams, different physical measurement techniques, different assumptions, different systematic errors, and instead of the values sliding toward each other, the way genuine measurements of a real physical quantity almost always do, they held their ground and dug in. Here is what should stop you cold. Measurement errors shrink with better instruments. That is the definition of a measurement error. This one grew. The scientific method's most reliable feature, convergence with better data, is failing on this specific question. Which forces the next question. What did we build our equations on? Modern cosmology stands on a 6-parameter model called Lambda-CDM. Lambda for the cosmological constant, the placeholder for dark energy. CDM for cold dark matter. Together with a handful of other numbers, this model predicts almost everything we observe at the largest scales, from the pattern of galaxies to the temperature ripples in the cosmic microwave background. One of those 6 parameters is the Hubble constant. Think of Lambda-CDM as a load-bearing wall. 6 beams hold up the ceiling of modern physics. Pull on any one of them and the ceiling shifts. The model tells us the universe is about 13.8 billion years old. It tells us the cosmos is made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. It predicts the sound horizon, the frozen echo of pressure waves in the early universe that shows up as a ruler we can measure in galaxy surveys. Every one of those numbers depends on the Hubble constant being what we think it is. The model is often described as a triumph, and in many ways it is. It fits an astonishing range of data with only 6 free numbers. But a triumph with a single point vulnerability at its foundation is still vulnerable. If H0 shifts, the age of the universe shifts. If H0 is not the same everywhere or at every epoch, the density of dark energy has to be re-derived. The composition of the cosmos itself moves. Now here is the hidden assumption most people never encounter. Lambda-CDM assumes the Hubble constant is constant. It assumes the expansion rate today is a fixed number that any correct measurement should recover. If it isn't, the framework isn't wrong, it's incomplete. And incomplete in a way that no parameter tweak can fix. That question stops being philosophy the moment you look at the data. The Hubble constant was never observed to be constant. It was assumed to be constant because the assumption made the equations tractable. Read that again. The word constant in Hubble constant is not a physical measurement. It is a convention. Physicists use H0 to denote the present-day expansion rate, the value right now. But the more honest quantity, the one that appears in the actual Friedmann equations, is h of z. The Hubble parameter as a function of redshift, as a function of cosmic time. That parameter has always been allowed to vary across the history of the universe. What Lambda-CDM adds is a specific prediction for how it varies, driven by a cosmological constant that never changes, and matter that dilutes as space expands. Plug in the model, and h of z at every epoch is locked to a single number today. Now the data is pulling on that lock. In 2024, the Dark Energy Spectroscopic Instrument, DESI, released results from its first year of galaxy mapping. The data hinted at something the cosmology community had spent decades assuming away. Dark energy might not be constant either. Its density might be evolving over cosmic time. The statistical signal is not yet definitive, but it is aligned with a growing pattern. If dark energy evolves, or if new physics enters before recombination, or if the Hubble parameter behaves differently in different epochs, the tension resolves. But only by admitting that one of the load-bearing pillars was mislabeled. Here is what this really means. The audience is not looking at a scientist's mistake. They are looking at a category error baked into 20th century cosmology. The universe was described with a vocabulary that promised stability the physics never guaranteed. And if the constant isn't constant, scaling the problem up breaks something worse. A 9% disagreement in H0 does not mean a 9% wobble in cosmology. That is the intuitive assumption. It is also wrong. The discrepancy cascades non-linearly. Take the age of the universe. With H0 at 67, the cosmos is about 13.8 billion years old. With H0 at 73, it drops to roughly 12.8 billion. That is not a rounding issue. That is a billion-year discrepancy on the age of everything. On when the first stars ignited. On how much time galaxies had to form. On the timeline of every cosmic event we date. Now shift to structure formation. The tempo at which matter clumped into galaxies depends on the expansion rate. Push H0 up, and the universe had less time to build what we see, which means the ingredients had to work faster, or the recipe was different. Then look at the sound horizon, the ruler frozen into the early universe by pressure waves. The Hubble tension pulls on that ruler. Baryon acoustic oscillation measurements, which are meant to be a rock-solid independent check, get bent by the mismatch. Small tension is narrative anesthesia. At the foundation, a 9% disagreement is not incremental. It is categorical. Physics has seen this pattern before. In the late 1800s, blackbody radiation refused to match classical predictions at short wavelengths. It was called a small problem. It became the ultraviolet catastrophe. It became quantum mechanics. Mercury's perihelion precessed by a few extra arcseconds per century, a tiny mismatch. It became general relativity. The last two times a small tension behaved like this, physics changed forever. Both cases share the same shape as what is happening now. A well-established theory made a precise prediction. Careful measurement returned a slightly different number. The community first assumed the measurement was flawed. When better instruments confirmed the discrepancy, the assumption shifted to unknown systematic effects. Only after every conventional explanation had failed did the field accept that the underlying framework itself needed to change. We are somewhere in the middle of that same process right now. The measurement has been confirmed. The systematic explanations have been tested and rejected. What remains is the harder step, accepting that the framework may need to bend. Which means you are not watching a fight over decimal places. You may be watching the front edge of the next revolution, or the exposure of a wall we haven't figured out how to climb. Step outside tonight and look up. The physics you just spent 5 chapters absorbing is not happening somewhere else. It is happening in the space between your eyes and every point of light above you. Space itself is expanding right now at a rate we cannot cleanly measure. The starlight arriving at your retina has been stretched by that expansion, redshifted. Every photon carries a fingerprint of the exact process cosmology is fighting over. Take Andromeda, our nearest large galactic neighbor, 2.5 million light-years away, calibrated against distance methods that depend on the Hubble ladder. Take the observable universe, roughly 93 billion light-years across, a number derived from H0 and cosmic time. Take the Earth beneath your feet, formed about 4.5 billion years ago, dated against a cosmic timeline that assumes the model holds. If H0 is variable, the universe you live inside is not the calm, well-mapped Lambda-CDM universe you were taught. It is a universe where the largest scale physics we know is quietly wrong. Think about what that means. The night sky is not decoration. It is a measurement instrument. It has been reporting an inconsistency for over a decade, and most people looking at it have no idea. The photons are honest. They travel, they stretch, they arrive. What we cannot do is agree on how much they stretched. This is not academic. It is the physics of the space you are physically inside, the physics of the distance between you and every star you have ever looked at, the physics of the light your eyes were built to catch. Every photon that reaches you tonight is old. It left its source when the universe was measurably smaller. On its way to you, the space it crossed expanded, and the photon stretched with that space. That stretching is the Hubble expansion, made physical, made local, made visible in the color of the light itself. The disagreement about H0 is not a debate about a distant abstraction. It is a debate about the exact amount of stretching that just happened to the light landing on your face. The disagreement is not out there in some equation. It is here, in the room, in the air, in the sky above your roof. And once the disagreement stops being academic, the institutional response starts looking strange. Every next-generation instrument built to resolve the Hubble tension has instead confirmed it. That is the opposite of the pattern any measurement dispute is supposed to follow. Consider what has been thrown at this problem. The James Webb Space Telescope, the most expensive science instrument ever launched, went to verify the Hubble Space Telescope's Cepheid distances. The crowding error hypothesis, the last plausible instrumental excuse for the high value, was tested and rejected. The distances held. Then the independent methods started stacking up. The tip of the red giant branch, mirror variables, surface brightness fluctuations, strong gravitational lensing time delays from the Holocaust collaboration. Even the first gravitational wave standard sirens, an entirely different physical measurement pathway, pointed the same direction. Local methods clustering near 73. Meanwhile, the early universe measurements held their own ground. Planck at 67.4, the Atacama Cosmology Telescope, the South Pole Telescope, all converging near the lower value. Two islands of consensus, separated by a strait no bridge has been able to span. Then, in 2024, DESI reported that dark energy itself might be evolving. Another crack in the same wall. Here is the interpretation you cannot avoid. Billions of dollars of instrumentation, designed explicitly to close this gap, have widened it. This is not a data problem. This is a physics problem wearing a data problem's clothes. The Vera Rubin Observatory is coming online. The Roman Space Telescope is being built. CMBS-4 will map the microwave background with unprecedented sensitivity. None of them will resolve the tension by being more precise. Precision is not the missing ingredient. New physics is. That distinction matters more than it sounds. When a measurement dispute is a precision problem, better instruments end it. When a measurement dispute is a physics problem, better instruments only sharpen it. Every observatory currently under construction was designed and funded under the assumption that this is a precision problem. The data coming out of the past decade suggests that assumption is wrong. The tools built to answer the question are now the tools proving the question cannot be answered by better tools. Which raises an uncomfortable question. Why is the public messaging still so calm? The cosmology community knows the tension is real. Public communications still frames it as an active area of research. That phrase is doing a lot of work. In a conference hall, active area of research describes a field where senior scientists disagree about whether their foundational model will survive the decade. In a press release, the same phrase reads as reassuring maintenance. Nothing to see, still being worked on. Adam Rees and the Shoes collaboration have been explicit for years. The tension is not going away, it is growing. Nobel laureate-level physicists have used words like crisis in peer-reviewed papers. Journal headlines have used them too. And yet the mainstream science coverage still tilts toward calm. Let me be clear about what this is and is not. This is not saying scientists are hiding anything. The papers are public. The data is public. The disagreement is documented in detail. This is not saying the science is fake. Lambda-CDM was and remains one of the most successful physical theories ever constructed. Its predictions match observations across enormous ranges of scale. This is not saying Lambda-CDM was useless. Every framework that gets replaced was useful. Newtonian gravity is still what we use to land spacecraft on Mars. What is being said is narrower and more specific. The communication register has drifted below the actual stakes. Institutional caution is a professional virtue. It is also an incentive structure. Grants, tenure, and public trust reward incremental language, not existential language. That structural incentive makes the truth arrive quietly. The scientists know. The papers say so. The public hears something softer. And once you strip the polite language away, what's left is not a small tension. It is a much larger question the field has been circling for a decade. The Hubble tension is not alone. Read it beside a growing catalogue of other cosmological anomalies, and the picture stops looking like a single, stubborn measurement dispute. It starts looking like a pattern. Consider S8, a parameter that describes how clumpy matter is at large scales. Measurements of the cosmic microwave background predict one value. Measurements of actual galaxy clustering and weak gravitational lensing return a slightly lower value. Another mismatch, another tension. Individually dismissible, statistically persistent. Then DESI. The 2024 and 2025 results hinting that dark energy density might be evolving, not constant. If confirmed, the cosmological constant itself, the lambda in Lambda-CDM, would need to be replaced. Then the CMB anomalies, the hemispherical asymmetry, where one half of the sky's microwave background is slightly hotter than the other. The cold spot, a region of anomalously low temperature. The so-called axis of evil, an unexpected alignment of low-order multipoles. Each anomaly, taken alone, could be dismissed as statistical fluctuation. Taken together, they are harder to ignore. Then, JWST's early universe surprises. Massive, well-formed galaxies appearing far earlier than Lambda-CDM predicted they should exist. The universe seems to have built structure faster than the model allowed time for. None of these anomalies proves Lambda-CDM wrong on its own. Together, they suggest something the field has been reluctant to say plainly. The model may not be wrong in one specific place. It may be approximate everywhere. And the Hubble tension is simply the loudest symptom. Think about how a scientific framework typically fails. It does not usually collapse from a single dramatic contradiction. It accumulates small mismatches across independent measurements until the pattern becomes impossible to explain as coincidence. That is exactly what modern cosmology is watching happen in real time. A cluster of tensions, each one dismissible, none of them going away. This stops being a measurement dispute. It becomes the possible boundary of 20th century cosmology. The same way Newtonian gravity was correct for everything humans could see until it wasn't. You are not watching a small argument. You are potentially watching the last decade before physics has to build its next foundational model. Which forces one last question. What does the verdict say? The Hubble constant may not be constant. Even if it is, the fact that our two best ways of measuring it disagree at over 5 sigma is telling us plainly that the model is incomplete. Not wrong, incomplete. And incomplete at the scale of the entire universe is not a small verdict. Look at what has accumulated. The tension has grown, not shrunk, for over 10 years. Every new instrument has confirmed the disagreement rather than resolving it. The other cosmological anomalies point the same direction. The institutional language has not caught up to the physical reality. Return to where this started. 2 instruments, Planck and JWST. Same universe, different answers. When you first heard it, it sounded like a technical curiosity. It isn't. It is the sound of a foundational assumption cracking under load. Consider how far the conversation has traveled. It began with a number, It ended with a question about whether our largest-scale description of reality was ever complete. That is what a real scientific crisis looks like. Not shouting, not scandal. A slow, disciplined recognition that the map and the territory are no longer aligned. The universe was never required to be constant. That was a hope, dressed up as a physical law that made the equations easier to write. The equations are now telling us the hope was premature. Here is the narrow room for hope, and only here at the end. This is not the end of cosmology. It is almost certainly the beginning of the next one. Every previous crisis in physics, from the ultraviolet catastrophe to Mercury's perihelion, delivered a deeper universe on the other side. What replaces or extends Lambda-CDM will not be smaller. It will not be simpler. It will be stranger. Step outside tonight and look up again. The photons hitting your eyes have crossed billions of years to get there. They have been stretched by a process we cannot cleanly measure. That is not a footnote. That is the physical fact of the space you live inside. You are living during the years when physics will either resolve this or admit that our largest-scale description of reality was always provisional. Both outcomes are historic. Neither is small.